So welcome to your first Build breakout. This is great for us because you're still not jaded, like after several days of breakout after breakout after breakout. You're fresh, you're energetic. And it's great for you because we are the only two people in the room who haven't seen the keynote, because we were getting our slides ready and stuff. And so what we want you to do, did we announce anything cool? All right. So your goal is to find us afterwards and tell us something cool that we announced at the keynote so we can be caught up. My name is Bill Barnes. I work at a part of Microsoft called Developer Experience.
My name is Micheline Harris, and I'm a software engineer and new member of Microsoft DX.
And former?
I'm a former developer, and after that, I was a data scientist, and now I get to be a developer again. So I'm really excited. Thanks.
So here's what we're going to talk about today. In Developer Experience, what we do is we sit down. We're developers. We're a pretty technical group. We sit down with developers from partners at companies like yours, and we help them solve hard problems, usually using Microsoft technology and sometimes not. And we take the feedback from that experience back to the product teams. And this is one of the ways that we keep making our products better. And one of the phrases that we have heard so many times over the last year is we'll be in the middle of a hackfest, and someone will say to us, and it'll be kind of like a secret, like, why does Microsoft keep talking about AI? Is that just marketing nonsense? They didn't say nonsense. And I had the same thing myself. So I just came back to Microsoft last year after a long time of not being a developer. I was actually a professional cartoonist, and I hadn't really been paying attention to what was going on in the field. And I came back, and even within the first few days, I kept hearing AI, 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 and I'm like, oh, they did it. Like somewhere in Microsoft is like an electronic brain, and it can answer any question, and it knows what you're talking about, and it can really get you. And then I found out it wasn't true, and I was just super disappointed. And I'm like, oh, it's just marketing nonsense, but I didn't say nonsense. And the thing is, the more that I looked into it, the deeper I got, I actually started getting on board with it. I started believing it, that we really are in the midst of a revolution. And what we want to do here today is, first of all, give you a definition of AI that I think we can all get behind, and put the marketing nonsense behind us. We're going to spend some time telling you how it works. We are hopefully going to get you excited about a lot of the things you can do with it, and we're going to give you some next steps, some suggested next steps on a path forward if you want to get into this whole AI thing. So I'd like to start with a story, and I want to say that I have permission to tell this story, which is a few months ago I was about to head to New Zealand to give a talk much like this, and my wife said, what are you going to speak about? And I said, I'm going to speak about our cognitive services. And she said, what's that? And I said, well, it's things like computer vision and understanding speech. And she said, oh, I know this. I've been reading about this. It uses AL, right? And I said, what's AL? And she's like, AL, I've been reading that. It's behind all of the new innovations in computers. There's Alexa, and there's Siri, and there's AL. And I said, oh, you mean AI? And she said, no, I mean AL. And I said, I'm pretty sure you mean AI. And she said, no, I mean AL. And she'd really gotten attached to this notion that there was this cute little character named Al that was behind all the really cool stuff going on in computers today. And my wife is very intelligent, and she used to work at Microsoft. But this is the tragedy of sans serif fonts. And I tell you this story primarily because now I can't see the letters AI together and not see Al, and I just basically wanted you to have the same experience. So here's a definition of AI. This is a little cynical. This is by someone who works at Microsoft, who actually may be in the room here today. Chris Bishop said, artificial intelligence is just whatever a computer can't do yet. So I think this is sort of true. I think this jibes with me, which is back when, in the dawn of computing, Alan Turing said, we'll know computer's intelligent when a person can be typing and won't know if they're talking to a computer or a human. And the problem with that is that humans are hilariously easy to fool. Because there was this program in the 60s called ELIZA, which was basically a little psychoanalysis program. And all it would do is just put your words back to you. And all ELIZA would have to say is, tell me about your childhood. And people would be typing for 20 minutes, and they'd be like, wow, the person I'm typing to is a really good listener. So then we said, well, we'll know computers are intelligent when it can beat a grandmaster at chess. And then that happened, and people were like, nope, that's not it. So we keep moving the goalpost, which is a little unfair to artificial intelligence. Poor Al. But I think this reflects the fact that many of us, our whole concept of artificial intelligence comes from the movies. It comes from science fiction. For me, AI will always be a magic black box that can do anything. And we're just not there, and we're not going to be there for a while. But my colleague, my friend Rick from DX, offers this definition, and I like this one. I've taken it to heart. He says, Artificial intelligence is computers doing things that we would normally think of as intelligent in humans. So the idea here is that humans do lots of things, and most of them do not require intelligence, and many of them do. And what separates us from the lower animals is the things we do that are intelligent, and that computers now do some of those things. Do they do all of those things? No. Do they do a large fraction of those things? No. But they do some of them, and they do more of them every day. So I offer this to you as a very reasonable definition of artificial intelligence, and based on that, we are already there, like we're off and running, and now it's just about more, right? So I first got exposed to AI back in the late 80s when I was at university, and I actually worked for a couple of AI researchers. And AI in those days, as they put it, it's just like teaching children. We're going to program in all these rules, and when we've programmed in enough rules, the computers will, I don't know, they'll sort of rise and achieve sentience or something. And it was like, if we want to teach them to understand language, we'll teach them about letters, and letters come together to form words, and words come together to form sentences, and we'll teach them about syntax and grammar, and eventually they would start understanding speech. CMU, even back then, was big on self-driving cars, and they had you would see little robots going down the sidewalks, and I'm pretty sure inside those self-driving robot cars was like, this green stuff is grass, and this gray stuff is the sidewalk, and you don't go on the green stuff, and you do go on the gray stuff. And they would just have all these rules, and they'd pile on top of each other. And again, they would say, it's just like teaching children. I'm like, that makes sense. It's just like teaching children. So then I left college, and I started computer science, and I never really did kind of touch AI again until recently. But the time came a while ago when I was about to have a child, and I thought, oh, it's going to be just like teaching children. I need to teach my child facts. And so I literally started reading a lot more nonfiction, because I'm like, I have to know all these facts to teach them. In fact, not just the facts, but I have to assemble all these facts together into a model. And then what I'm going to do is I'm going to take this model and I'm going to put it in my child's head. And with this model, the one that I've carefully developed for my child, they will grow up to be a doctor, lawyer, astronaut, president. Those are union operators, just so you know. So it turns out this is not how children work. And I'm pretty sure the people I worked for back in the 80s had never met a child before, because it's a lot more like this. It's a lot more like children hear things, they see things, they touch things, they smell things, they certainly taste things. And based on all that, they build up their own model of the world, which I have very little influence over, as it turns out. And based on that model, that's what influences their behavior. And if I don't like their behavior, I can offer different sensory input, but all of parenting is basically trying to craft the right combination of sensory input, because we have no control over the model. Weirdly, we cannot just open up the brain and start reprogramming them. Too bad. This is how people work, and even back in the 40s and 50s, the early version of computer scientists started saying, well, I guess we should probably do stuff like that. Back in the 40s, we had drawings of neurons, and they actually made an artificial neuron in the 50s called a perceptron, and then they gathered a bunch of them together, and they called it a neural network. It was a really good idea to try to emulate, the way brains work, at least so far as we understand how brains work. The only problem is it didn't work. So they shelved it. We're going to shelve it, but it'll come back, so hold on to that thought. So this notion that what's going on is that people actually infer the rules of how the world works based on the input they get is how machine learning works. So I apologize if the slide scared you. I showed it to several of my colleagues, and like the biggest, strongest guy was like, that's a scary slide. So it's like this. The data comes in, something magical happens, and the computer infers a model of how the world works based on that data, and that influences its ability to answer questions. So this is more or less accurate, but Micheline is going to go into slightly more detail on how it actually works. So this morning, we did catch a little bit of Harry Shum's part of the keynote, and he talked about, in China, this great work they did with machine learning and retinopathy to diagnose diabetes based on photographs of retinas. So what Micheline's going to do is walk us through how would we actually go about doing something like that.
Thanks, Bill. So as a former data scientist, just for a brief time, I learned a couple things. And one of them I learned is to ask very specific questions. So the question that was asked in the case of what Harry Shum was talking about, remember it was about diabetic retinopathy and patients with diabetes and diagnosing whether they have a diseased eye or not. So I'm going to use the label diseased, not diseased. So the whole goal here is to talk about a model. And with this model, I want to kind of step back and go back in time to the old days and describe how I would have done this as maybe as a developer before as a data scientist. So imagine, if you will, I'm like in a hospital and I'm following doctors around and jotting down, like, these are doctors that are actually diagnosing patients with retinopathy, so disease or not disease, right? So I'm writing down all these notes. Like, how are they doing this? What rules are they using? What decisions are they making, right? And so I'm doing this, I do this with like several doctors. I'm just following them around all day long in the hospital, writing. And I end up with this list of rules. Like, these are the decisions all the doctors made to decide whether this eye was a diseased eye or not. And so as the programmer, I'm like, hey, I'm going to write a cool program that's going to encode all of this information and be able to predict disease, not diseased. Be able to basically label like something that's new as disease or not. So I do this, and I end up, say, with like 10,000 lines of code because it gets really, really complicated, and I've got a lot of cases that I'm taking into consideration and merging what one doctor says versus another doctor. So it can get really, really, really complex. My code base is just huge, and that, to me, is like, oh, golly gee, that's a debugging nightmare, right? So at that point, I think to myself also, so I've got this rule-based program, right? It's a rule-based system. And there's other things that occur to me after the fact, like, hey, these doctors, they actually have some sort of intuition, right, about these retinograms, about the eyes that they're looking at. How do I encode intuition, right? Like, how would I go about doing that? So I'm actually literally missing some information. I'm missing something that might be significant that the doctors know that I cannot actually code into this rule-based system. So a different approach. So here we are, we're writing this code, we hit a wall. And the wall is a wall of accuracy, like how well we can do. So machine learning can actually break down that wall for us. And it's a different way of thinking, and it's a different way of doing things. So in this case, with machine learning, I actually begin with data. So I begin with, and in this case, it's a really large data set. It's like close to 100,000 images that have been, conveniently for us, we actually asked these doctors to come along and label all of these images as diseased, not diseased. So instead of the developer, right, like going to the hospital and following doctors around, we actually just say, hey, like, will you label these images, right? So at that point, I've got some data, I've got a great question, right? I introduce an algorithm. So an algorithm is simply some mathematical construct, doesn't matter too much, but an algorithm is what I train. So I give it a bunch of data, and we call it training. And this data that we feed into it is actually called a training data set. And so after we train the algorithm, we end up with our model. Okay? So the model literally can take input. It is a mapper, and this is just the way I like to think about it. It's a mapper to some labels, to some output labels. So it takes some input, it's a mapper to output. Literally, you can just think of it in this way. So we get some new data, we have some new retinograms the doctors have provided for us from patients, and they can separate out based on this, using this model that we've already built into two different groups, right? Diseased, not diseased. So one thing I didn't tell you guys is that I actually held back some of that data, and that data that we originally used, like we originally collected our input data, so I held back some of that. And we know what's really cool is that we know the answer. So the question for me with this model, we've got a model, so what would the question be here for me is that how well is this model actually doing? How do I even test that, right? Well, I mean, I just answered my question, really. Like, I've got some test data, and I know the answer to it. So what's really cool about machine learning is we can test our models. And we can measure them with things we call metrics. So in this case, let's go back to our example of the diseased, not diseased eye. Perhaps we have, so one of the metrics is positives, false negatives. Okay? So a false negative is when it's actually a diseased eye, but it's classified as healthy. So we're trying here, to prevent blindness in patients with diabetes. So maybe that's not, having a few of those is not acceptable to us. So we can look at that as our metric. We can look at the false negatives and say, hey, let's try to minimize these false negatives. Let's decrease the chances of getting these guys. So one way in which we can do this, and there are lots of ways in data science that we can do things, but one way, and as like the data scientist coming back to being a developer, my brain is still warped with data science, so I apologize. But I would go back to that original data set. And in that data set, there's a lot of clever things that like the data scientist can do. One of them is to look for things like, is this data cleaned up? Are there missing values? And all sorts of like attributes of the data. So we can clean up the data, we can do all these things. So what? What does that mean? How does that even matter? So what we're really getting at is we want the most significant parts of the data in order to train that algorithm to create the best model we can possibly create, right? So now we've basically gone through this data science process. It's actually an iterative process, so we can go around and around and try to increase the accuracy of this model. How good is it doing? We test it with our metrics. We improve upon it. Another way in which we can improve is pick a different algorithm of the same class, train that algorithm with the data that's now like clean and nice. So we have a lot of options here. When I first came to being a data scientist, and I'll probably talk about this a little bit later, but the math part really, the algorithms, right, like really intimidated me. And in fact, to be a data scientist, you don't really have to be able to write a machine learning algorithm. So, when I came to data science, that was actually like a very, very big problem for me as a developer. How do I go about learning this? How do I learn all this math? So, yeah.
Not too bad.
All right. So we just spoke about this case of classifying things, classifying is diseased or not. So there we go. That's actually one question we can ask of machine learning of a whole bunch of different questions. So another question we can ask is sort of a predicting the future question. So I was looking at like a news article, and I saw that, oh my gosh, like sea levels are rising globally, right? So I was thinking, well, I wonder how they're going to, I wonder what's going on, and how in the world do we predict how much sea levels are going to rise with all of this data, right, that's coming in from like NOAA and places like that? How are we going to predict how much sea levels are going to rise? Perhaps like I want to know as an urban planner where I need to build buildings, right, or where I need to think about infrastructure, or maybe even disaster planning. So, so one way is using a class of algorithms called regression that do regression. And in that way, it's pretty cool. We can literally predict the future. Okay? And a lot of you are probably like, I know regression. That's great. Like, that's machine learning, guys. Like, you're already doing it, so you're good. So another thing oh gosh, boy, this one really like kind of freaked me out. So I was like, it's actually like very much not a laughing matter, but I was reading about how malware is being implanted in embedded medical devices like pacemakers. Like, yeah, this is really happening. And so we have this malware being implanted, and this is what they're actually doing. Like they're holding people's data ransom. So there's data transmission that happens in these embedded devices, and it's being intercepted using malware. So like literally, it's data hijacking. So researchers are like, oh my gosh, right? Like us, we're like, oh my gosh, how do we prevent this? And maybe not how do we prevent it, that's like a future question, but how in the world do we even detect this? This is wild. So one way in which we can do this is look for like blips in energy consumption, electromagnetic radiation, and even that like data transfer. We can look for little like aberrations, right? Little blips, little dips or spikes. So this is another class of machine learning algorithms called anomaly detectors. Yeah. So another like machine learning question, and this is a super cool thing. So there was last December, it made a big splash. Bless you. They made a really big splash. It was a machine that could play the game of Go. I don't know if you guys have played Go before. I actually haven't played. I've only have looked at it and studied it a little bit. But it's actually in orders of magnitude more complex than chess. It's a really complicated system, right? If you were to think about doing it in a rule-based way. Like that's nearly impossible. What they actually did was they created this machine, this model, they call it AlphaGo. So AlphaGo beat a world champion, Lee Sedol, at the game of Go last December. And this is being considered a huge feat of AI. And it may sound like, oh, it's a board game, right? But once I started reading about what was going on, I thought this was really cool. It actually got better. Like, it got better at the game by playing against instances of itself. So I thought that was pretty wild. So yeah, like it improved over time by playing against instances of itself. And that's an example of a class of algorithms called reinforcement learning. That's an example of reinforcement learning. Yeah.
Oh, can I tell my story?
What? OK, fine.
So my story is, I was in New York last week at a Hackfest, and I had read my book on the plane, so I got there and I had no book. And I went to, there's so many great bookstores in New York, but instead I went to the Barnes & Noble in Times Square, because that's where I was, and I was being lazy. And I bought a book. It's called Big Little by John Crowley. It's great. And I didn't notice till I got home and looked at my receipt, but there's a little receipt, and it said, if you like this book, you might like these 5 other books. And I looked at them, and I'm like, I do like those 5 other books. Like, Barnes & Noble has my number. And actually, they didn't know it was me. I paid by cash, and yet somehow they have linked these books together. How did they link those books together?
So there's the final class of algorithms, final question we can ask is basically, how are things related? And how does Netflix work, right? How does online dating work? This is using recommender systems. So yeah, it's pretty cool stuff.
The thing about these 5 questions is they demonstrate the power of machine learning. And I think some of the things that can get lost, because of course we're glossing over it, is this is essentially stuff you cannot do with traditional computer science. I mean, I think we can understand that we can do regression in Excel, but Excel can't do planet-scale data. Just computationally, it just explodes. What you need to do is create these models that have already distilled all the important parts of the data so that when you run it on new data, it's very efficient. And that process of training, which is very computationally expensive, is the hard part. Actually, I think maybe we announced this morning, I heard we were going to, a service that lets you train models up in the cloud so that you don't have to invest in tons of GPUs and stuff like that. So that's the hard part. And so all of this stuff is essentially things that we cannot do today with traditional computer science. So this is if you needed a good reason to get into AI. So let's talk about this, right? Let's talk about AI software. So imagine this blue rounded rectangle is the universe of all the software that satisfies this criteria. 20 years ago, this would have all been rule-based, but over the years, more and more of it has been taken over, if you will, by machine learning. And there's been a recent entry. Remember this little purple guy? It turns out the purple guy's working now. It wasn't working then. They just needed to reinstall Windows. It was great. No, what was missing was three things. We needed math. We needed just more math, really great matrix stuff, combinations of stuff that we just didn't have in the 50s and 60s. And we needed data. We needed a lot of data, a lot of data. Neural networks, table stakes might be hundreds of thousands of data points, more typically millions and billions. Imagine in the 60s what it would take to even create billions of items of data. How would you transmit it? How would you process it? Of course, and that's the last part, which is we just needed the ability to crunch through this data. And so that has been the transformation. It's the same technology, new techniques, lots of data, lots of horsepower. So here's an example of a neural network and an example of how the technology is moving very quickly. And so maybe you remember this. So this was 5 years ago now. Google announced that they had written a neural network that could identify cat videos. I mean, they did go for the hardest, most important problem. And it's amazing. And in fact, it was not even training data. It actually did this itself by, I don't know, it was magic. It's all magic to me. It took them 16,000 CPUs and a team of a dozen or so people, but they got it, and it was pretty amazing. What you may not have heard is that 3 months later, another team from Google, 3 people, did the exact same thing, same accuracy, on 2 GPUs. And the difference was the technique. They used a convolutional neural network. So that is transformative changes just by essentially different algorithms. It really makes a big difference. The other advantage is accuracy. That for relatively small amounts of data, traditional ML and neural networks get about the same accuracy. But then traditional ML kind of tops out. But neural networks will keep getting more accurate with more data. And that's why we keep throwing more data at it. So very briefly, an example of a neural network would be face recognition. So the way this works is there's layers. That's the deep. In deep neural networks, there's a depth of layers. So this one layer is a recognizer that all it recognizes is edges. It knows edges. The next one takes those edges and it puts them together, and it puts them together into facial parts, ears and noses and, I guess, mustaches. And then only then will the next layer be able to put those pieces together into faces. And so we layer the stuff, and they all take advantage of the stuff that's going on underneath, which is kind of an amazing and wonderful technique. And the Microsoft Face API does this, and if you've ever played with it, it's pretty cool. It just puts a little red box around your face, and it says there's a face. So up till now, we talked about these questions it can answer. Neural networks have another trick up their sleeve. Because of the depth thing, they can start to add and subtract essences of things. We can have neural networks that can identify the writing style of Hemingway and translate an essay that you write into Hemingway speak. And it's pretty good, and it'll only get better. We can now take apples and turn them into oranges, and oranges into apples. And if this seems like a trivial example, just remember the last time you were having a conversation with someone and you made a comparison and they said, that is not an apples to apples comparison. Now it can be. So I think as a person coming relatively new to AI, it's easy to just look at what we have now and say, it's still just a bunch of tricks. And I always think of this quote. It's one of my favorite quotes. I've heard it many times in my career in computer science. We tend to overestimate the effect of a technology in the short run and underestimate the effect in the long run. We just have to accept now, I have to accept anyway, and I want you to believe that, that this AI thing is just unstoppable. It will just keep getting better and better and better, and the things it can do and do well are just increasing. And so it comes down to this, which is the way we will make software is not the way we have made software. We have been studying computer science, and this new thing is empirical science. It's literally a different science. And all the buzzwords are different. We have to learn all new buzzwords. I came back to software after 10 years, and I had to learn some NoSQL, and I had to learn React, but basically it was all the same. I mean, I'm like, it's just computer science, same stuff I did in college. Really not that much has changed. This is entirely different. And it can be incredibly intimidating. Like, that's a lot of buzzwords to learn. I don't know what your buzzword acquisition rate is, but still, that's a lot of them. And so The thing to accept is that it's not all or nothing. You do not have to learn. I'm not sure how many there are. I actually literally sent an email to Micheline saying, give me all of your best buzzwords and I'll put them on a slide. You don't have to learn them all at once. It's not all or nothing. Let's go back to the goal. The goal is, here's this universe of software, this universe of software that's intelligent. You want to make your software intelligent. So there are ways we can help you without you having to make the full jump into data science. For one thing, we have these cognitive services. They're really good, and they're getting better. One of the things we didn't quite talk about with these models is you tend not to just generate a model and then sort of walk away from it. You tend to just keep coming back and adding more data, especially for the neural networks. And our cognitive services are getting better every week, every month, and we keep adding them. We added like one a month. I think maybe in the keynote, did they talk about the custom vision, the custom image recognition? And it's really good. We have a general purpose computer vision API, and it's good for like aiming at a table, and it does incredibly well. Like I see 2 bottles of wine and a pair of glasses and a laptop. But the fact that it's good at generally recognizing stuff means it's not so good at distinguishing very subtle differences. And so if you want, for instance, to identify pictures of your company's products that people have posted to Twitter, you would like to have a more specific model that can do that. And that's what the custom, they just renamed it, the custom vision service does. Is it allows you to train on your own data, and so do something that's more useful for you. And you didn't have to learn a lot of data science to make that happen. And this is true about the cognitive services. There's ones you can just make a REST call and you're done. Like it immediately works. Like Bing speech to text immediately works. If you want more accuracy, if you want to train speech to text that uses vocabulary from your domain, that uses the accents from where you live, that maybe uses the acoustic signature of people calling on landline phones, you can train on that, and now it becomes more accurate in that domain. So there are APIs that will reward you for the amount of effort you put into them. And it's a kind of an 80% thing, an 80-20 thing, right? There are probably cognitive services that will do a lot of what you want to do, and at some point you are likely to hit that wall, and now it's time to roll up your sleeves and to get your hands dirty and learn some data science. So what does that look like? What does it look like for us going from developers to being data scientists? I happen to know someone who recently made this transition, and she's going to tell us how she did it.
Yeah, so like Bill said, the cognitive services are fantastic. It's just a REST API call for most of them. So as a developer, like I can wrap up all my logic for the cognitive services in this way. So coming from being like a developer, then a data scientist, now a developer again, I just want to tell you a quick story about how I went through that transition from developer to data scientist. And this is just to let you know that it's kind of the iterative process of data science, but it's also the iterative process of Micheline, where she goes and what she does. So basically where I started was by going to these data science conferences. And at the data science conferences, I actually learned a lot about these packages that were popular, that were really great at like helping people do data science. They don't do it all for me. I did have to know a little bit, so I had to learn a little bit of domain knowledge. But really, like, I just picked a package to begin with. I picked a package like that sounded great. I literally stalked GitHub for a little while to find out like which one was being, we all do that, right? So at that point, all these packages, they come with sample data, they come with like the docs, right? But this one that I chose is called scikit-learn. That's not necessarily important, but it came, like most of them, with a lot of tutorials and a lot of guides to get me started very quickly. Like there's some where you can do a neural network. It's literally like, start creating a neural network, get a neural network like done end to end in 5 minutes. So a lot of these packages have fantastic, quick ways to get started. So that's how I started in that process. And then I used a lot of the visualization tools in these packages to look at the data, right? Because we're all like switching to this paradigm, or at least I was switching to a paradigm where I was more data-driven. Like my life was literally living in data. So I started looking at the data, visualizing it, and then I started getting curious about that data, and I could ask my own questions. So at that point, I started saying, hey, maybe I could like create my own feature from this one and this other one, and maybe I can find something that's more significant, right, in the data, build a model that represents like what's really going on in this data. So at that point, I then see how well is Michelin doing at this? How well is this process going for me? So I take a look at, like we were talking about the metrics, right? So how well did I create a machine learning model? I can literally just use the package to calculate some accuracy, some precision, the buzzwords that we were talking about. But we all kind of understand like how well is something doing. So I was at that point, right? And the next step for me was, like I said, this was an iterative process. So not only did I get to learn this fantastic package, I got lucky in picking a really good one, but honestly, there's so many great ones out there. But I got the opportunity to actually teach scikit-learn to 200 folks a year later. So it didn't take like a terribly long time to really, like, for me, learn a package well enough to teach it to people. And we all know the best way to learn is to teach, right? So that was a good measure of me, my ability to do data science. And like 2 days ago, I was actually talking to a friend of mine, and he said he had started using Azure Machine Learning Studio. I've been using and talking about Azure Machine Learning Studio like at Microsoft for a little while, and what was really cool is like he said he actually finally understood that data science flow, that data science process, the data, the cleaning the data, the algorithm, how it all fits together, how all the pieces fit together by using Azure Machine Learning Studio. And I had that exact same experience. And so after I learned this one package, I moved on to Azure Machine Learning Studio, and I really got like a great like taste of data science. Like I actually really started grokking data science at that point. So that's really like the flow that I went down to get better, to iterate on it, to get better, and then yeah, like.
It made you the goddess you are today.
Oh, thanks, Bill.
So here's our advice. You didn't ask for it, but here you go. Start with the cognitive services. There's a lot of good stuff there. They may actually solve your problems. You might be done. But my advice is don't be done. Even if it's really solving all the problems that are immediately in front of you, my advice is to go farther down the path. And I think that Azure ML Studio is a great way to do it. And I'm not just saying that because I'm here speaking at Microsoft Build, but because it is sort of like VB was 20 years ago. It is this amazing visualization of stuff that brings in a lot of non-professionals and makes them productive. Start to go through this process. Play with data, visualize data, run models, look at the results, tweak stuff, change stuff, see what it does. Do it for a little while. Do it for long enough to find out if you like it. I didn't used to be a database guy, and I'm like, databases, that sounds boring. And then I played with a database for the first time, and I'm a database guy. I never not want to do databases, and I still never not want to do databases. And it's that way, it may be that way for you, or you might just look at this and be like, not my cup of tea. And that's fine, but find out. Now you know. Now you know whether this is a path you want to go down or not. And you've got something else too, which is now you have this vocabulary to work with these new people who are going to be in your life. The next step, and we're going to spend no time on it today because it's really vaulting forward into the future in terms of the time and the expertise you have to put into it. But Microsoft has stuff that rewards the experts. Microsoft ML was recently open source. Basically, a bunch of internal ML tools written in R are now open source. And then our cognitive toolkit, which is our neural network, or one of our neural network kits. So this is just a path for you. And again, I encourage you to take it. And I guess that leads me to, so let's talk about what you can do while you're here at Build. Other talks. There's a lot going on, and I just cherry-picked some. That doesn't mean the others aren't good. It means I just had something to say about these. So first of all, my colleagues Ryan and Matt are going to be talking about bots. Bots is where I spent most of the last year of my life. And we've learned a lot. We've worked with over 100 companies on Hackfest, helping them develop bots. We really did a bad job at the beginning. We do a somewhat better job now. Bots are new. We're still figuring it out. And they will share kind of the cutting-edge best practices on that. Just this afternoon is an open Q&A. We're going to have questions here in just a minute. Feel free to ask us, but I bet that Q&A will have more expertise and be able to answer the questions that I'm sure we can't. Speech recognition, and we've got this new custom speech recognizer is really helpful, and it's one of the things that can be done really, really badly. speech recognition, you can really make a hash of it. So it's great to get some more information on it. Kind of ditto with computer vision. The Bing APIs, they're called the Bing APIs because all that data comes from Bing. It's not just random branding, like there's a reason for it. And there's a lot of good stuff in there. If you're interested in deep learning, we really only touched on it today. There's going to be a talk Thursday at 2, a general talk on cognitive services Thursday at 4, but just come with your specific questions about the cognitive services you care about. And then Friday, now I don't know if they finally put the title out, but there's essentially some cool AI stuff having to do with security, and they wouldn't even tell us what it was. It's just blocked out in the schedule, so I'm super curious, and I put it on there because I'm super curious. So we're going to end this talk by talking about a relationship that for many of you may have just started right here in this talk. And it's the relationship between AI and you. And actually, since we're talking about a relationship, let's not call it AI, let's call it Al. Al sounds like someone you could have a relationship with. Al he may have just started working at your company. He may be just about to. He hasn't been working there long, I'll tell you that. He's young, he is full of excitement and ideas, and he came out of school with all this crazy stuff that you don't really understand. So what are you going to do with Al? Are you going to close your door and hope Al goes away? He's not going away. He's like super stubborn and determined, and doesn't understand that you closing the door means you don't want to talk to him. You could mentor Al. You could probably teach something to Al, and in the process learn something yourself. I think what will happen for many of us, this is happening for me, is that you will find this kind of accommodation with Al. So I have the opportunity right now, which is very exciting, that there's a new deep learning product that we're starting to spin up at Microsoft, which I can't tell you about, but hopefully I'll come back next year and tell you about it. And it's super cool. I'm going to try not to say what it is. And so the partnership we have is that some people from my team are going to be working on the SDK. We're going to be working on the training UI. And then the people from the deep learning team are working on the deep learning, and we're working together. And already I am finding out more about the deep learning world, and they are finding more about what developers actually want in an SDK. And that partnership is really important. The more I understand about what they do, the better, and vice versa. So this relationship is a two-way relationship, and I encourage you to greet it with open hands. Al's a good guy. You'll like him. So I think with that, we should probably, first of all, thank you for coming out here. We know you had many breakout sessions to choose from, and we thank you for choosing ours. If you want to take off now, you can. Otherwise, we could take questions for a little while. If you do have a question, will you please stand in front of the mics, because we're recording this so the folks at home will be able to hear you. Thank you. I know, lunch is next. What can we compete with? Sir.
Yes.
Hi, I'm Brian. I'm from 3M.
Get a little closer to the mic.
You got it? I'm from 3M Company.
Okay.
And this is a target-rich environment.
Yeah.
You know, in a company like ours.
Actually, let's just wait a couple of minutes and let everybody file out who's going to file out. Because Brian's about to ask a really good question, so if you want to file out, that's totally up to you.
Please stay, Brian.
Brian at least is going to stay.
Yeah. I think it's a little quieter.
We'll just give it a minute to get quiet again. Nice. There's a Visual Studio update download today. You weren't going to write any code today. All right, 30 more seconds, and we'll take your question. All right, Brian, be loud. We'll try to do our best.
Thank you. In thinking about how to get to know Al a little bit better.
Yeah.
In large companies like mine, where there's no shortage of problems to solve, can you give me sort of a profile of how to pick the best problem? Because there's too many to choose from.
Yeah, so that's actually a really great question. Like, how to choose the best problem. Like, basically where to start, like, which problem to even solve. So most of the machine learning that's happening out in the world is actually this classification, one bucket versus another, of labeled things. So that example, we used with the disease, not diseased. Almost always we're mapping input data to two buckets. So that's where I would start, is like a classification type of really what we call like experimenting. So kind of playing around with some data that has like some information tagged to it, and then splitting it into the groups and picking like, an algorithm to do that. So that's actually like the place I would start, is pick a really good classification example. Should we go back to that slide?
Yeah, I was thinking that a great way to help yourself essentially brainstorm the answer to that question would be to look at those 5 questions. And a lot of the business problems we face can be solved. The security, for example, I don't know what our special AI security is thing, but anomaly is huge in security. In fact, that was the example we brought up, which is how do we know this is malware? We probably don't want to pull out your pacemaker and see if it's running malware. We have all these signals, and these signals are kind of attenuated, and we as humans really can't see it at all. But amazingly, the machine can. They can see the patterns, and then we can say, this is what good software looks like, this is what malware software looks like, and now it can recognize the difference. So it's to start looking for these patterns around these questions that you can ask.
And really, like the key I would say is to ask the most specific question you can. Just be really, really specific to keep your problem space as small as possible, and then you can expand from there.
And also to let the sky be the limit and not censor the questions you're asking, because I know I can't do that. Like it's crazy how much we can now do. So ask the question you really want to know. And maybe we can't answer it, and me and Al, maybe we can't answer it, but maybe we can. So ask, if the question is, what are sales going to be, in 2020 if we change the name of this product? I don't know, but maybe ask the question and see if something can happen.
Is there another question?
So given clean data and a good understanding of the problem you're trying to solve, are there tools that could help you pick the right algorithm within the model, I guess?
So to be very technical, yes, there are actually tools that will pick an algorithm for you. It's kind of a new realm. I was reading about this one tool that could generate code, like machine learning code, and pick an algorithm for you. I wouldn't actually recommend doing that, but I've used this. It's called the algorithm cheat sheet. If you just search for it online.
Oh yeah, it's great.
It is amazing.
It's just a flowchart.
It's just a flowchart.
It's like a flowchart, like should I eat this cookie? Right, but instead it's which algorithm should I choose, and it just asks some very simple questions about the type of problem you have and the type of data you have, and it gives you a family of algorithms.
Right, they're just yes/no questions. Is this data large? Is this data labeled? And it takes you to the class of algorithms that you should focus in on.
Yeah.
Yeah, yeah. It's in the context of Azure Machine Learning Studio too.
Mm-hmm. Right.
So, yeah, great question.
Yeah.
Thank you.
You're welcome.
So, kind of the opposite of what the last question was. A lot of these talks start presupposing that you have clean data and good data. Do you have any advice for how to get to that point, especially as with...
You should clean your data.
Yeah, right. I keep trying to tell people, but...
Amazingly, we were talking about this, but we all know how to do that part. We've all scrubbed data. We've all have data that came in the wrong format, and this is a number in a text field and stuff like that. All of those skills you have apply incredibly well, and they're really not that different. It is all about scrubbing the data and using the same tools you would use for databases.
Yeah, checking for types and seeing weird values that don't make any sense. The basic math, averages, standard deviation. Maybe look for some outliers.
Yeah, you can. Visualization can really help. If you can graph stuff, then you can start seeing what your outliers are, and are what the hell's that?
Yeah.
So just spend the time.
Just spend some time in the data.
Yeah.
That's pretty much the gist of it, right? Yeah. Good question.
This might iterate off of the last question, but
iteration is what we're all about here, machine learning.
We hacked on Liberty Mutual chatbot last
right?
August. Yes.
How you doing?
And good. And one of the questions that we had Lewis models, and we were trying to pick which Lewis model we ought to be using. And without having human interference to make that decision. How close are we to being able to do something of that nature?
To go do it, I would still do it in the build my own logic to route to the proper Lewis model. I know that there are some tricks. Maybe use the Q&A maker, which is one of the new. I think it was announced last November. The Q&A maker will take a frequently asked questions, and distill it down, and then you can use your facts and the answer to that to route to a Lewis model.
Yeah.
So I've done that before.
That we are doing sort of building stuff around that. The problem is when you have two different models, they calibrate differently.
Yeah.
And so this one you could feed the same utterance to both of them, and this one says 93%, and this one says 97%, but it doesn't really mean anything because they're different models, so those things don't correlate. Yeah, still a hard problem.
Hello.
Hey.
So in this slide that we have here, after this, you showed a few slides later that the thing that's improved over the last 20 years or so is that we have massive compute capabilities. Are there still compute or processing challenges that these algorithms run into?
I guess what you're saying are, in terms of generating models, are we still compute bound on certain models?
Exactly.
Are we?
See, at this point, the sky is almost the limit. Because like at Microsoft, we have the Godzilla clusters, the G class, and these are GPU machines, and we can just scale it really as much as we want and create as many clusters of these GPUs as we wish.
Yeah.
And it's just a matter of, at that point, how much money you want to spend, really. So, yeah.
Yeah.
You're welcome.
Yeah, and there's custom silicon coming now. Yeah, this stuff's just only going to get easier, faster. Good.
Hi, and I apologize if this question was already asked because I was in the overflow room and came down.
No problem.
My question is ML versus AI. Where do they overlap? Where do they diverge?
I'm going to bring up my slide. Oh, look, it's the next slide. They overlap. So AI is this whole class of software that basically does intelligence things. And a lot of it, increasingly, in fact, I think that is now too small, is being done with machine learning. And increasing amounts of that, and that is way too small, is being done with neural network, which is really just a kind of machine learning. Yeah.
Thank you.
You're welcome. Sir.
So if all of these machine learning algorithms or AI algorithms are truly mathematical models, how do we take something like string data and kind of input that or use that as an input into running some algorithm?
It's cool. I'll just say the way we don't do it now. The way we don't do it now is we don't parse it. We don't try to understand, in this case of English, we don't try to understand English, which is what we were trying to do back a million years ago when I was in school. Now we just kind of throw these things at the algorithms and they chop and dice the strings into what are called features to try to figure out what is important about them. Sorry, that's buzzwords. Do you have a better way to say it?
No, I think that was actually a perfect way of saying it, Bill. Thanks.
Sorry, it is buzzwordy. For instance, so one of the things that Lewis does, which is our language understanding service, is what it's doing is it's weighting words. There's a lot of words in the English language, right? There's tens of thousands, I'm going to guess. And it's trying to figure out which are the words that are important in terms of deciding what you're trying to say. So it's actually just a giant linear equation with coefficients on every single word in the English language. And so all it needs to do is break stuff into words. And then it just runs that stuff on your training data. And then usually it's not very many words that are important. And those words, more than anything, will determine how it groups those utterances. But the same thing applies to images. Amazingly, these techniques are all more or less the same things. Images are just bits. You chop and slice and dice into different size things, and you start looking for what's important.
Yeah. Basically, we're encoding the information, right, like an image, each pixel, into almost like just an array. You can just imagine it. It's just a vector, just an array of numbers. Mm-hmm. So, yeah.
Now let's start switching off. Go ahead.
So now that we kind of have these sort of commodity algorithms to do these sort of common tasks, from what I remember, a lot of the danger with neural networks is you get into this overtraining problem, where your network gets so specialized and so good at detecting one thing that now you're basically not able to solve the original problem. You end up on these little kind of local maxima in that graph. So kind of within these sort of public algorithms and such, is there anything that's sort of being done to sort of say, wait a minute, okay, we got to dial back and retrain and sort of regeneralize the algorithms, or is that still a danger that you guys find in some of the kind of public stuff?
Yeah, actually, that's a great point, because I think there's a danger in every single algorithm that we use. And it's really because they're data-driven. So they're only as good as the data we give it. And with neural networks, it actually takes us through a process and gives us a result based on some input. But that process goes through some layers and filters, and we might get overfitting, and it only recognizes dogs like poodles, right, or something. It's a poodle recognizer, and it can't recognize anything else, just that. So what we do is actually there's a way to give feedback to our neural networks and say, hey, you're doing a good job, you're not. Just like we were talking about with the metrics, it's a little different with neural networks. But essentially, we give it like a way to detect its own error. Right. So a way just for it to give it some feedback. So it detects its own error, and then it kind of trickles back and says, hey, you need to readjust some things, Mr. Model, to make it work a little bit better. So that's a great question.
Okay.
Yeah, I was wondering if you had a...
A little closer.
How's this? Oh,
Thank you.
That's good. I was wondering if you had a specific opinion or a pointer if someone came to you and said, okay, well, the problem I have is wanting to compare documents, getting a document and seeing out of a universe of samples which one it looks the most like.
An opinion about what?
Anything, how to get started, a Microsoft service that is well suited to that.
Do you have
Anything at all.
recommendations on that specific scenario?
It's funny you use the word recommendation, Bill. Because I would use some sort of recommender system. So something that deals in relationships. Just be careful that, with machine learning, we're doing predictions, we're doing groupings. So if it's just a matter of pattern recognition and stuff like that, we can not hard code it, but we can write programs to do that. But the power of machine learning comes when we're grouping things based on something that may not be very obvious, something that might be very subtle, or we are predicting the future. So.
Yeah, I think of ML being used on data we haven't seen yet, rather than just analyzing a bunch of data we have.
Yeah.
Thanks.
You're welcome.
Hi. Back to images. For say the retina, how many images did you guys need to, have in your initial data set to train it? Are we talking hundreds or tens of thousands?
That was about 100,000?
Yeah. It was close to 100,000 retinal scans. Yeah. And that was a few years ago, so they probably have quite a bit more now. Yeah.
So I got a chance to go to one of these Microsoft labs that they did. And what I understood how you guys, I understood that the data that they feed for training, I understood the control data that they use to sort of check it. What I didn't understand is that where does the machine learning actually store some of that, not your data, but its learning data?
That's a great
Where
question.
is that being stored?
It's encoded into the model itself. So a simple way to think about machine learning, and this isn't so much true for neural networks, is again, as just a big equation, coefficients on variables. The variables are each part of this thing that I could independently identify, like the color, the size, the length. By the way, tell me if I get anything wrong. I only learned this yesterday. So when you go through those 100,000 images, you're basically trying to come up with what are those coefficients. Should this number be larger? Should this number be smaller? And and this is her word, we wiggle those numbers up and down until the results of going through that equation put the things into the right categories.
So we minimize the error that we're getting based on what we know.
So they are really
being sort of stored as the model, and that's it.
The data itself is essentially
it's irrelevant at the end of the day.
Yes, absolutely. It has gone through a chipper. And there's
so
not much left.
once that's fixed up, then all you have to do is just feed it new data and ask for answers.
Isn't that awesome? Yeah, that's it. That's it. That's why they're so fast. And that's the big difference between training your model, which has to go through a lot of data, sometimes billions of points of data, in lots of permutations and combinations, and running a model where all that stuff has been distilled to sometimes just a few numbers.
Yes.
Considering my company is moving towards using AI and big data, all the other buzzwords from that slide of yours, and then relating to your curious story of transitioning from being a developer to a data scientist and then to a developer again, as a dev lead, what type of development profile shall I be looking for? So is that a ratio between data scientists and developers, or is that like?
Are you talking about hiring, or just kind of how your team should be
Yeah.
spending their time?
Or is that this super kind of developer type called Al that kind of amalgamates data scientists?
Look, data scientists aren't all that. Al is a good guy. He's not necessarily any smarter than us. He's just had a different focus. Fair enough?
I'd say fair enough. Right now, there are a lot of like data science degree programs and certificates, so you could look for that. But I'm not. Well, I guess I have actually hired data scientists before, but I looked mainly and with all of my colleagues for people that are good self-learners. Because to be honest, like I actually taught myself all that I needed to know for my job as a data scientist. I taught myself like a lot of, like we all do, right, new programming languages as a developer. So that, I don't know, like that's my 2 bits is like a really...
Yeah, from my very small sample size, they're just a little nerdier than normal computer scientists.
Right. So they're more like T-shaped people.
Yeah, people that
do
can
both
teach
things.
it. Yeah, that's a great, yeah, actually.
But hiring is a very difficult problem. I don't think we can solve it here today.
Great. We need a better model.
We do.
Yeah.
Anyone on the side? Okay, you, sir.
Maybe one last question.
So if you
Yeah, I think we're just about, we are out of time, so let's answer your question and we'll be done.
Oh, okay. All right, so if you've got you need a new algorithm for something that, is it pretty much impossible if you're launching, say, a new sales program and you want to see which things people will buy, that you just need to sell a lot of it first?
You're talking about where does the data come from for something new?
Yes.
Yeah.
Yeah, you do need a big data set for a recommender system, sometimes.
And then the follow-up would just be, so if you're at a point where it's like, okay, it's good enough to launch, but we want to keep improving it, how do you actually do that for production environments? And so you need all of the trained data to train the model, and it's hard on your database, right?
And you need to ask the right questions.
Yeah, if you're extracting all the data to train it, if it's your production data, how do you do
Right,
that?
because the training process can be like lengthy, time-wise. But you would.
I think that sounds like a hard problem because you're basically saying, if there's some hypothetical new thing we developed, would people like it? Like that's hard to get data on.
Right. I'm just saying though, if you're at the point where okay, it works well enough, but we want to keep improving it.
Yeah.
It's really costly to train.
Yeah. No, that's actually like a really good point. And I know that when at least I've been using Azure Machine Learning, I've been hooking it up into a pipeline with Data Factory and bringing in any data that I want, really, like IoT data, et cetera, et cetera. And I can use Data Factory, which is one of our products on Azure, to sort of pipeline that data to an Azure Machine Learning, what they call experiments, which is just like the model. But we can also set it to retrain itself. And so that's how people have been doing this in a production environment. Like,
Got it, okay.
We can retrain pretty easily within Azure Machine Learning.
Okay, so
Yeah.
just piping the data and then in its own place asynchronously keeping it.
Yeah, exactly. Yeah, like lots of instances of Azure Machine Learning basically are happening, and it can be retrained like continuously and iteratively, like in your pipeline.
Thank you.
I didn't understand any of that. Always more to learn. Thank you all for coming out this morning.
Yeah.
Enjoy lunch.